Hello everyone, my name is Miguel Ángel Zambrano Arjona. I represent the Facultad de Ingeniería at the Universidad Autónoma de Yucatán and the Institut des Nanosciences de Paris at Sorbonne Université. Today I will present our work titled Corner and Edge Modes in Gallium Nitride Nanomembranes, a complementary spectral window for near-field radiated heat transfer. To understand the scope of this research, we must first look at the dual nanoscale regime. In this regime, both the membrane thickness and the vacuum gap fall well below the thermal photon wavelength. When this happens, radiative transport is no longer carried by the flat surfaces. Instead, it concentrates at the geometric singularities of the membrane, namely its corner and edges. Prior work has shown that in silicon carbide or SiC membranes, these corner and edge modes can account for up to 81% of the total near-field radiative heat transfer. However, a fundamental question is, does this generalize to other polar dielectrics? To answer this, we choose gallium nitride, or GaN, as our natural test case. GaN is a compelling candidate because its dielectric function is described by a well-known Lorentz oscillator model, which has thoroughly characterized due to its central role in power electronics, high electromobility, transistors, or HEMTs, and solid-state lighting. Furthermore, GaN supports surface phonon polaritons within its Red-Strahlen band, specifically near 14 to 18 micrometers, and this provides a complementary spectral window that is resonant far from that of SiC, making it highly relevant to thermal management in GaN-based devices. Our methodology consists of investigating the fundamental corner and edge electromagnetic modes in GaN nanomembranes with thicknesses of 20, 50, and 120 nanometers. We perform finite element eigenvalue simulations using the well-established dielectric function of GaN, computed the dispersion relation for each thickness, and directly compared them with the equivalent modes in silicon carbide membranes of the exact same geometry. When analyzing the modes, we observe that as the thickness decreases, the corner merge into an edge mode. By placing the results side by side, we found that the GaN modes exhibit higher confinement. This can be explained through the dispersion relation, revealing how the lower surface phonon polariton resonance frequency of GaN relative to SiC reshape the model structure in the dual nanoscale regime. Additionally, we note a shift in the degeneracy of the modes, and this degeneracy shift is attributed to the intrinsic properties of the material itself, showing that this point is a material dependent but completely thickness independent. So, thank you so much.